Today we talk about semiconductors. Now let us see the energy level diagram. The insulator, semiconductor and conductor. If you compare, the forbidden energy gap between the valence band and the conduction band is the largest in insulators and it is overlapping in the conductor. Semiconductor is in between. Semiconductors are of two types, intrinsic and extrinsic semiconductors. Intrinsic is a pure semiconductor. Extrinsic is of two types, the N-type and the P-type. Intrinsic semiconductors. Now you have the silicon crystal. The silicon has 4 atoms. It can either be silicon or germanium. It forms 4 covalent bonds with the neighboring silicon atoms. This is the intrinsic semiconductor. Now let us see the extrinsic semiconductor. Now if you have a silicon crystal, if the process of doping is done and one of the silicon atom here is shown as replaced by arsenic, that way many other are replaced in a single crystal. So if arsenic is pentavalent impurity, it can either be phosphorus also, the another example. So one electron is a free electron. So like this you have lot of free electrons which is available for conduction. Conduction is due to the negatively charged electron, hence it is called N-type semiconductor. Since an electron is donated, this impurity is called a donor impurity. Now let us see the P-type semiconductor. Here one of the silicon atoms shown is replaced by a trivalent impurity, either aluminium or indium. There is one less electron. This absence of an electron is what is known as a hole. That is a positive charge. Conduction is due to these holes which can accept an electron, hence it is known as the acceptor impurity. Now let us see a PN junction diode. This is the block diagram of a PN junction diode with P-type and N-type on both the sides. This is the PN junction. So for a PN junction diode, P-type semiconductor is not joined with the N-type semiconductor, but one side of a single crystal of silicon or germanium is doped with acceptor P-type impurity atom and the other side is doped with the donor N-type impurity atoms. The junction formed is called the PN junction. Terminals are attached to the PN junction regions, PN regions, and crystal is covered with a plastic material. This is the potential barrier which we are going to talk now. Then we have the symbol of the diode. This side is positive, this is negative. So let us talk. Free electrons on the N side diffuse or spread everywhere. When a free electron diffuses across the junction, a positive ion is produced in the N region. Soon after entering the P region, the free electron combines with a hole. Therefore, the hole disappears and the associated atom becomes a negative ion. Thus, each time an electron diffuses across the junction, a pair of ions is produced. Thus, a small part of P region near the junction is negatively charged and a small part of the N region becomes positively charged. This region is called the depletion layer or region. The depletion layer stops further diffusion of free electrons across the junction. The depletion layer acts like a barrier. The difference of potential across the depletion layer is called the barrier potential V0. This is also called the internal potential barrier. Its direction is from N region to P region. This potential barrier stops further diffusion of holes and electrons. The potential barrier for germanium diode is about 0.3 volts and for silicon diode is about 0.7 volts. Now let us see what is forward biasing of a PN junction. This is the block diagram again. The P side is connected to the positive terminal. When the positive terminal of a battery is connected to the P region and the negative terminal is connected to the N region of the junction diode, then the diode is said to be forward biased. When potential difference is greater than the barrier potential, electrons travel from the N region to P region. At the same time, electrons enter the N region from the negative terminal of the battery. Therefore, a continuous current is set up in the circuit. The conventional electric current flows in the opposite direction to the motion of electrons. In forward bias, the resistance of the diode is very low and the diode acts as a closed switch. The potential barrier is reduced and current flows. So this is a reduced PN junction. This is the direction of current. Now let us see what happens when a PN junction diode is reverse biased. That is, the positive P is connected to the negative. So there is an increase in the depletion layer. So when a positive terminal of a battery is connected to the N region and the negative terminal is connected to the P region of a junction diode, then the diode is said to be reverse biased. The free electrons in the N region are forced away from the junction towards the positive terminal of the source. Holes in the P regions move away from the junction towards the negative terminal. Therefore, the width of the depletion layer increases. The depletion layer stops increasing when its difference of potential equals the source voltage and the current does not flow through the junction. In reverse bias condition, the resistance of a diode is very high and it acts as an open switch. In practice, very small current due to minority carriers are produced by the thermal energy. This is the IV characteristics of a PN junction diode. This is the forward bias characteristic. This is the current on the x-axis and the voltage on the y-axis. This is the reverse bias, lower one. We can see the knee voltage for about silicon is 0.7 volts. Zener breakdown or avalanche breakdown is about 20 microamperes for silicon. This is the reverse breakdown voltage. We will talk about this again next time. So in our next session, we'll discuss how forward biasing and reverse biasing of semiconductor finds its application in Zener diodes, rectifiers, LEDs, solar cells and transistors. Thank you.